Today we will discuss on Chapter 5, Work, Energy and Power. So in this video, we will continue with the subtopic 5.2, Conservations of Energy. Okay, so we start with the first questions. An object which is 5 meters above the ground is released from rest. So meaning that the initial velocity is equal to 0. Determine the speed of the object when it is 3 meters above the ground. Okay, so meaning that initially we are at the height of 5 meters from the ground. Okay, after that we want to find what is the speed when the object is 3 meters above the ground. Okay, initial velocity is equal to 0. So when it reaches 3 meters above the ground, what is the velocity? Okay, so we label it as point A, and this one we label it as point B. So based on the conservations of energy, we know that the total energy before and after is still constant, is the same. Okay, so we write it as E initial is equal to E final, the total energy. Okay, so the total energy here involves kinetic energy plus potential energy. Similar for final energy, there are kinetic energy and also potential energy. Okay, so initial energy actually we are referring to point A, where point A initially we don't have kinetic energy. Okay, because initial velocity is equal to 0, and potential energy, we have potential energy because it's above the ground 5 meters, so it's mg, h is equal to 5. So when you reach point B, where point B is 3 meters above the ground, we have kinetic energy is equal to half, and v square, v is the value that we want to find, plus mgh, where h at that moment is equal to 3 meters. Okay, so we can simplify it, become 5 mg equals to half mv square plus 3 mg. Okay, so we can cancel off m. So finally we have 5g minus 3g equals to half mv square. Okay, then half mv square will equal to 2g. So finally our v will equal to 4g square root. Okay, so try to press calculator where our 4 is times 9.81 square root, then you will get the value. So you will get 6.26 meters per second. Next, we go to questions number 2. Okay, where questions number 2 involves smooth surface, meaning that there is no frictional force. We don't need to do extra work to overcome the frictional force. Okay, so here we have, let's say I label it as point C. This is point C, this is point A, this is point B. Okay, so we know that at point C, point A, or even at point B, the total energy are the same. So the total energy at point A is equal to the total energy at point B, and also equal to the total energy at point C. So now, when the object is at point C, the velocity is equal to 10 meters per second, and the height is at 5 meters. Okay, so we want to find the speed where it reaches point A. So we can compare C and also A, because we know that total energy at point C is equal to total energy at point A. Okay, so at point C we have we can write K initial plus U initial equals to K final plus U final. Okay, K initial here is half mv square, and initial velocity is 10 meters per second. So we substitute 10 meters square plus potential energy mgh, where h at point C is 5 meter, equals to, at point A, kinetic energy is equal to half mv squared, and at that moment kinetic energy is maximum because all the potential energy already convert into potential energy already convert to kinetic energy. Okay, so we know that at that moment actually the velocity is maximum. So later we need to find out what is the value. Okay, of course it will greater than 10 because initial is 10, so of course just later our velocity at point A will greater than 10 meter per second. Okay, plus mgh. Okay, so when you reach the ground, h is equal to 0, so we just substitute 0. Okay, so we can simplify it. Okay, we can simplify it, become 100 over 2, so it's equal to 50m plus 5 mg equals to half mv squared. Okay, so we cancel all m. So finally we will get our v is equals to 50 plus 5g. Okay, here we have half. We have half v squared. Okay, so you can bring it. Okay, you can bring it. Our v will equals to 250 plus 5g 9.81 square root. Okay, so press calculator, you will get the answer. So the answer is 14.07 meter per second. So this is the velocity at point A. Okay, so as I mentioned just now, because at point A the kinetic energy is maximum because all the potential energy already convert to kinetic energy. So therefore the velocity at point A is greater. Okay, it's 14.07. That is greater than just now 10. Okay, next we want to find the velocity at point B. Okay, so you can take either you compare A with B or you can compare C with B. Okay, so maybe I will try to compare A and B. Okay, A and B. So we know that energy at point A is equal to the total energy at point B. So at point A we only have half mv squared, where v just now we get is 14.07 square, so remember to square, and we don't have the potential energy because at point A there's no height. Okay, equals to kinetic energy at point B is half mv squared. This is the value that we want to find, the v, and plus mgh. So at point B, h is equals to 3. Okay, so we can cancel off m. So finally, we will get half 14.07 square equals to half v square plus 3g. So you can rearrange back your equation. Half v square equals to half 14.07 square minus 3g. G is 9.81. Okay, so you can rearrange back. Okay, so after you press calculator, you will find that velocity at point B is equals to 11.8 meter per second. Okay, so if you compare at point B, the velocity at point B is smaller than A but is greater than C, because C is at the higher position, so the velocity is smaller than B. Next we go to questions number 3. Okay, questions number 3 involves spring, but for these questions there's no frictional force. Okay, so questions number 1, 2, 3, no frictional force, so we don't need to consider the work done to overcome the friction. Okay, so for questions number 3, an object of mass 2 kg is placed 2 meter directly above the top end of the vertical spring as shown in the figure. The spring has a spring constant, so this is the value K, the spring constant. Determine the maximum compression undergone by the spring when the object falls on it. Okay, so if let's say I label this one as X, okay, so we can label it as, we can divide into 3 positions. The first position A is at the maximum height. Okay, at the second position I label it as B, where it is just above the spring. And the third position C is when it reached the maximum, when it compressed the spring. Okay, so we have 3 positions here. And we know that the total energy for A equals to total energy at B and also equals to total energy at C. Okay, so total energy before and after is constant. Okay, just that maybe the energy will transfer from one type to another type. So now we want to determine the maximum compression undergone by the spring when the object falls on it. Okay, so you can take A, because we want to find the maximum compression. We want to find the value X when it reaches C. We want to find when it reaches C. So either we can take A compare with C. Actually, it's much more easier. Okay, so I will take total energy A equals to total energy for C. Okay, of course you want to take B and C also can. B and C also can. But one thing is B and C, later your kinetic energy, you don't know what is the value. Okay, so it's much more easier if let's say we compare A and C. So I will take total energy at point A is equals to the total energy at point C, where A, okay, we write K plus U initial equals to K final plus U final. Okay, so K initial, when the block is at top, there's no kinetic energy, so we just ignore the kinetic energy. And at that time, potential energy is maximum, where our potential energy is equal to mgh. Of course, h here we are referring to the total distance from the ground. So our h here is 2 plus x. Okay, the total from the ground. And when you reach point C, kinetic energy, because it's already maximum compression, so meaning that there's the motion already stopped. Okay, because already maximum cannot compress anymore. So kinetic at that time at point C also equals to 0 because already maximum, there's no any compression. Okay, tak boleh bergerak lah, sudah compress sampai tak boleh bergerak, sudah maximum. Okay, tak boleh pergi lagi. Okay, already maximum. So kinetic energy also equals to 0. And at that moment, our mgh also equals to 0 because already reached the ground. Okay, almost reached the ground. And we have half kx squared because we have elastic potential energy. Okay, we don't have the gravitational potential energy, but we have the elastic potential energy. Okay, so we can write the equations. 2mg plus mgx equals to half k is 500 x squared. So we need to rearrange back. This is a quadratic equations where we can write it as 250 x squared minus mgx minus 2mg equals to 0. Okay, then you can substitute all the value inside. 250 x squared, m is 2. Okay, so we can substitute 2 times 9.81. X is the value that we want to find, minus 2, m is 2 kg, g is 9.81 equals to 0. Okay, so finally we will get our equation will become 250 x squared minus 19.62x minus 39.24 equals to 0. Okay, so you press calculator, you found that actually your x maximum, the maximum compression is equal to 0.437 meter. Okay, so you can press calculator using the quadratic equations. Then you will get the answer. X maximum equals to 0.437 meter. Okay, next question, questions number 4. So for these questions onwards, question 4, 5, 6, it involves the frictional force, meaning that we need to consider the work done to overcome the frictional force. a child with the mass m rides on a irregular curved slide. Height, this is the height, where the height is 2 meter. The child starts from rest, meaning that the initial u is equals to 0. Determine the speed at the bottom, assuming that initially is no friction, is pressure, meaning that the first question we don't need to consider the frictional force, so it's much more easier, where I label it as at the top, I label it as A, where at the bottom I label it as B. Okay, so we know that the total energy at point A will always equals to the energy at point B. Okay, so K initial plus U initial equals to K final plus U final. K initial, of course, is equals to 0 because initially is at rest. Potential initial is mgh, where h is equals to 2 meter. So when you reach the ground, when you reach point B, kinetic energy is maximum. So we need to find the value m plus mgh. Okay, but at that moment, because already reached the ground, h is equals to 0. So therefore, we cancel. 2g will equals to half v squared. Okay, so your v, you will get the answer for v is equals to 6.26 meter. Okay, so this is the value that without frictional force. Okay, without frictional force. Okay, next one is if the force of kinetic friction. So now we need to consider the kinetic frictional force, where we need to overcome the frictional force, meaning that there is an energy loss. Okay, energy loss due to the friction. Okay, add on the child, how much mechanical energy does the system lose, meaning that what is the work done that we need to do to overcome the frictional force. So we need to find the work done. Okay, so what should we do is similar, total energy at point A is equals to the total energy at point B. Okay, but for this time, you must take kinetic energy plus potential energy plus work done. Okay, so this work done is to overcome the frictional force. Okay, equals to K final plus U final. Okay, so kinetic energy as usual is equals to 0. Potential energy is mgh, where h is 2 meter, plus this is the value that we want to find. This is the energy loss due to the friction. So we just leave it, the work done due to the friction equals to kinetic energy, where kinetic energy is equals to half mv square plus potential energy. So potential energy also equals to 0. So we just put it 0. Okay, so our energy loss is equals to work function, work done to overcome the friction. So it's half mv square minus 2mg. Okay, so based on just the questions already give us, assumes that V final, if there is a kinetic energy, kinetic frictions, our V final is 3 meter per second and m at that moment is 20 kg. So we substitute into the equation, half m is 20, V is 3 square minus 2, m is 20, g is equals to 9.81. So the answer that you get is equals to negative 302 joule. Okay, so why negative? Negative here shows that the energy is lost in the system. Okay, so negative here meaning that the energy lost in the system. That's why you will get negative. Okay, next we go to questions number 5. Okay, a child, okay, and a slide with the mass of 50 kg slide down a hill with the height of, so the height here is 0.46 meter. If the slide start from the rest, so again start from the rest, u equals to 0, meaning that there's no kinetic energy, and has a speed of 2.6 meter per second at the bottom. So when you reach here, the velocity is 2.6 meter per second. How much thermal energy is lost? Okay, so this time it's not because of the friction, it's because of the thermal energy. Okay, due to the frictions. Okay, so because of the friction, so that's why it already convert into thermal energy. So what is the work that friction does? So we need to find the work done due to the friction. If the heel has the angle of 20 degrees above the horizontal, what was the frictional force? So here we need to find two things. The first one is to work on the friction. The second one is the frictional force. So again, I label it as A and point B. Okay, so the total energy at point A when it's at the top will equals to the total energy at point B. So we write again K initial plus U initial plus the work done to overcome the friction, because this is the questions where there's energy loss, equals to K final plus U final. So K initial, there's no kinetic energy, and the potential energy initially is mg, H is equals to 0.46, and then work on the friction is the value that we want to find. Okay, equals to K final. K final is equals to half mv is 2.6 square, and the potential is equals to 0 because already reached the bottom. Okay, so we arrange back our equation. Our work done to overcome the friction, or the work loss, the energy loss, is equals to half m is 50, half mv square minus mgh 50 times 9.81 times 0.46. Okay, so if you press calculator, you will get the energy loss. So that's why you get negative 56 joule. Okay, so negative here means that the energy is lost due to the frictions and already convert into thermal energy. So this is part 1. Okay, part 2, you need to find the frictional force. So our work to overcome the friction. Still remember our subtopic 5.1, work to overcome the friction is F as cos theta. Okay, so our work to overcome the friction, the work done is negative 56. Okay, so you must substitute in the negative as well. And the frictional force is the value that we want to find. Okay, S here. Okay, S here is the displacement. So this children, this child, it will slide downward. Okay, so this is our displacement. Okay, and we know that the height is 0.46. So we need to use trigo to find. So this is our S, and the angle is 20. Height is 0.46. Okay, so we can use sine theta or sine 20 equals to 0.46 over S. So therefore our S we will get S that we get is equals to 1.345 meter. Okay, so here we will not round off yet because later final answer only we round off. Okay, so you just substitute inside S, the value is 1.345. Okay, cos. Okay, cos here because the motion is going downward. Okay, the motion S is going downward. Of course, the frictional force is opposed. Okay, frictional force is upward. So the angle between them is 180. Okay, where cos 180 actually is negative 1. So our F is equals to negative 56 over 1.345. Cos 180 is negative 1. Okay, so little negative, you can cancel off. So therefore, you will get 42 Newton because frictional force is in Newton. Okay, next one. we'll go to the last questions. Okay, last questions here is there's a frictional force. So the coefficients of the frictions between the 3 kg block and the surface is 0.4. So this is the value mu. If the system starts from rest, calculate the speed of 5 kg ball when it has fall at a distance of 1.5 meter. Meaning that initially this is the ball is at this position. Okay, so after that, when we release 5 kg ball, of course it will pull downward, and 3 kg object, it will go to the right. Okay, so what happened is this ball will go downward. Okay, so meaning that the object initially at here, okay, so it will go 1.5 meter to the right, and the ball initially at here, okay, initially at here, so it will go down. Okay, it will go down by 1.5 meter. Okay, so this is the final location for the ball and the object M1, M2. So, okay, next, calculate the speed of the 5 kg ball when it has fallen a distance of 1.5 meter. Okay, so in this system, we have two objects. So when we have two objects, we need to consider both. We need to consider both. So based on the conservations of energy, so the initial kinetic energy plus potential energy equals to kinetic energy plus potential energy final. Okay, and of course, because there is a friction, so we need to consider the work done as well to overcome the friction. So initial, the object here, the ball is at the height of, okay, if let's say this is the final position is 1.5, so the ball is actually at above, okay, above, let's say this is a reference point. If this is a reference point, okay, if this is a reference point, meaning that initially there's no kinetic energy because initially it's at rest, so no kinetic energy for M1 and M2. But potential energy, ball, if let's say this is a reference point, this ball, okay, this ball is actually above the reference point, so it's M2 G H is 1.5. Okay, if we, let's say it will refer to this reference point. Okay, plus the work done. So work done is equals to our F S cos theta. Okay, after that, final, when you reach the, okay, and when you reach the reference point, meaning that this ball will go down and this object, it will move to the right. So actually M1, M2 are moving together. Okay, are moving together. So our half mv square here, our m, we need to consider M1 and also M2, 3 kg plus 5 kg v square. Okay, and the potential energy, because this ball already reached the reference point, okay, so just now is at the top, so now it already reached, okay, the reference point, meaning that the H is equals to 0, so we don't have the potential energy. Okay, so we don't have the potential energy. So now we want to find the velocity. Okay, M2 we have is 9.81, height is 1.5 plus, okay, frictional force we don't have. S we have, because S here is because of initially the object is at point here. This is the point initially. So when we release, it will pull to the right. So when we pull to the right, the frictional force will add to the left, the frictional force. Okay, and this is the distance 1.5. So we know that the distance displacement here is 1.5, and cos must equal to 180 degrees because it's in opposite directions. Okay, it's equals to half 8 v squared. Okay, so before we want to find v squared, you need to find the frictional force first. So when you want to find frictional force, of course we need to go back to chapter 4, where we need to use the resultant force to find. Okay, so now we need to draw the free body diagram for this M1. So when you want to draw free body diagram, you must ask 5 questions. Okay, weight, normal, tension, friction, and F external. Okay, so weight number 1, yes, we have. Normal, yes, because it's contact with the table. Tension, yes, because there's a string. Frictional force, yes, we have the frictional force, okay, is to the left. External force we don't have it because there's no pushing or pulling. So now what should we do is we need to find the frictional force. The frictional force is at x component. So since it's at x component, so we write at fx equals to ma. Okay, where a is not equals to 0. Okay, a is not equals to 0. So we need to find fx where our tension, okay, because it's to the right, so it's tension minus friction equals to ma. Okay, but the problem is we don't have tension, we don't have friction, also we don't have the acceleration. So the first equation we just leave it because we cannot solve. Okay, let's just try y component. Okay, why we use y component? Because we know that frictional force, they give you the coefficients, the mu. Okay, so frictional force also equals to mu n. Okay, so we know that if the first equation x component we cannot find the frictional force, we can use the second method F equals to mu n, where mu equals to 0.4, and n you can use y component to find. So for y component, we have normal, force, and also we have weight. Okay, so we can take normal minus weight equals to 0. Okay, because this box is not moving up or moving down, it's only moving to the right. So right, there's a motion, but y component, there's no motion. Okay, so it's equals to 0. So therefore our n here is equals to mg, where m is 3 kg, g is 9.81. So finally we get our n. The value for n is 11. Sorry, it's not equals to 11. It's equals to 3 times 9.81. Okay, so I press calculator. So you get 29.43 Newton. So you substitute inside here 29.43. Okay, so times 0.4, the coefficient. So you will get 11.77. Okay, Newton. Then you substitute back 11.77. Okay, so you rearrange back the equations. Okay, you rearrange back the equation, you will find that the v, okay, at when it fall down to 1.5 meter is equals to 3.7 meter per second. Okay, so that's all for today. See you in next video. Thank you very much, and see you again. Bye.